Hello YouTubers. What we're gonna do today is go over another statics problem, and if you've seen any of my other videos, you know that I do care about y'all students out there. And so this is gonna be another simple 2D statics problem. So before I get started here, while I sketch out this picture that I'm gonna have, um, I want to tell you guys, let's see, I went to school. I graduated with a BS in aerospace engineering, and I do have a math minor. Um, so I've been hired for my academic ability to help tutor you guys online, and my sponsors are the owners of Contest Celebration. And what Contest Celebration is, it's a website that hosts picture-based contests and they give away $500 each month. Um, and so they're very, very nice people. They've actually I've met with them before. They have their office hours up on their website, and you can contact them anytime. So feel free to go to their website and create a profile and get on there with your pictures and see if you can win $500. It's a lot of money. Not something I would pass up. So yeah, you gotta check it out. So anyway, so here's our statics problem really quick. See, let me draw in our angles right here, and let's say this is a cement cylinder tube, very, very big. Let's say a crane's moving it, or somebody really, really strong, or whatever floats your boat, so to speak. No pun intended. So let's say what we want to find here. Let's say we want to find the smallest angle that these chords can be at to sustain this weight. Let's give the maximum tension. So I'll just say, yeah, tension max. Let's say that the maximum tension in these chords here can only be 800 pounds. Snowman 8s, 800 pounds. And let's say this cement cylinder they're using for construction. Let's say that weighs. We'll go with 900 pounds. Just have some nice clean numbers. Now they may not fall clean, but that's what we can go with. So what I need to do now is I need to assume that the magnitude of the tension in this chord and this chord AC, chord AB, is 800 pounds. And then write all my equilibrium equations and find out what the smallest possible angle can be. So, see what we're gonna do. So I can redraw this, make it a little bit easier. So we know right off the bat that the tension here in this chord is gonna be the same as the weight. It doesn't break up into components or nothing. It's gonna be the same. So see, this is gonna be this knot here. So we've got a force that's gonna be 900 pounds pulling up. We know that because of equilibrium. So one going up, got weight going down, and this is 900 pounds. So now we can get to solving. So the angles here, they are identical. They are the same for this problem. This goes right here down the middle. If it didn't, this wouldn't be 900 pounds. So angle theta. So for this to be in equilibrium, this isn't moving, it's not spinning, it's not gonna break. We're gonna write our equations out for the x and y direction. So let me go ahead and define our generic reference frame. This is it's probably one you guys are used to for this problem. And again, you could actually use any reference frame you wanted. it would change your numbers around only because it changed the angles, but the magnitudes would actually be the same. So if I say I rotated this by 15 degrees, this point of reference, and I could in fact do that with all these, I would just have to add that in for the angle when I run through my calculations. So let's sum the forces in the y direction, and we know it equals 0 because this isn't moving. It's just going to be hanging there. Say the crane broke down or something like that, or it's just hanging from the ceiling, or a really strong industrial ceiling. So some of the forces in the y. So let me make sure I write in the points here. So we've already said that we're going to assume that that these cords are at the maximum tension. So the force of AB and the force of AC, both those are going to be equal to 800 pounds. So we write this out. So we have to break both of these forces that go along the cord, obviously, into their components for x and y. So we're gonna, if you look here, we go with say we're looking at the sum of forces in the x direction. Well, we can see there's only two components, and those two are going to be equal but opposite. And if we follow that through, and if we follow that through, we can see that we're going to get 1 equals 1, because this force is the same, this force is the same, this angle is the same, this angle is the same. So setting those aside of the equal sign, that's what you would see. So it wouldn't tell you anything as far as what you're looking for, because you're looking for the angle here. And actually I can show you that too. So if we say we decide to sum the forces in the x direction. So we would have force AB times cosine of angle theta, which is, we don't know this yet, but that's the FAB cosine theta is the x component, okay, and that's pointed in this direction, which is opposite of my point of reference. And we know ropes, cords, and chains can only be in tension, so it's going this way. So continuing on with the equation, plus force AC times cosine theta equals 0. So we know I can move this over here and start plugging in numbers too. So if I bring this over to the other side, say I add this term, I add a positive force of AB times cosine theta to this side. I have to do the same to this side, add to that side. So I end up with force of AC times cosine theta is equal to force of AB times cosine theta. And right off the bat, I can divide both sides by cosine theta, so these cancel out. And FAC equals FAB. Well, we already knew that. We already said that up here. It's 800 pounds. So let me draw my little squiggly line so we can continue on with work. I like to save paper. So let's sum the forces in the y direction. Now that we've seen that solving for anything in the x direction doesn't help us with what we're looking for. So we got 900 pounds going straight up. So 900 pounds plus, oh wait, no, not plus, it's going to be minus, because these are pointed down per my reference frame. So minus force of AB times the sine of angle theta minus force AC times the sine of angle theta is equal to 0. So I'm going to rewrite that down here where I have more space. But we know already that this force is equal to this force, so we can combine like terms right there. And I'm going to plug in this 800 pounds right here too as well. So we have 900 minus 2 times 800 pounds times the sine of angle theta equals 0. So now we need to isolate theta. That is what we're looking for, to find the minimum here. So let me write up here theta min. Make sure we know what we're looking for. And so if you solve this, so you move this to the other side, you get 900 is equal to 2 times 800 pounds times the sine of angle theta, and divide by this 2 times 800. Well, looking at it, we know it's 1600, but I like to keep things apart when working with fractions. That way you don't do any multiplication or division that you don't need to do because it's already broken up. So equals sine of theta. Now to get theta, you have to apply the inverse sine. So theta is equal to inverse sine, and the way you notate that is like this, or you could say arc sine. Some people like one way or the other. I typically use inverse sine, and no, this isn't sine to the -1. So we can break this fraction down. We can factor out the 100 times this 9, because that's what 900 is. 900 is 9 times 100. Same for this one, is 8 times 100. So we can factor out that 100, right? And I believe that's it. So we have 9 over 2 times 8 is 16, and inverse sine of that will be our answer. So let me see if I can get on my trusty calculator and go from there. Let's see. Alright. Gonna start plugging this in, and we'll see what we get. So that's 9 over 16. I'm plugging this in right now. 9 over 16 is equal to 0.5625. Let me write that down. So inverse sine of 0.5625. And that angle there equals batteries died again. I think I need a new calculator, or maybe just new batteries. Arc sine 0.5625, and that'll give me 0.5974 radians. Now, this is in fact the answer, but people don't really have a scale for radians. You couldn't go outside and say, hey, make this angle 0.59 radians. You couldn't say that to a construction worker. He's gonna say, hey, I got a protractor, man. Give me a real number. So we have to convert this, and the way you convert this is just by multiplying by, let me see, I don't want to say the wrong number here. Still messing around with my calculator now. Man, this thing is really messing up. So, what you want to do is multiply by 180 degrees over pi. And that, in fact, will give you, almost wrote the wrong number there, give you the answer you're looking for. So that's going to be, and I'm going to Go back to my trusty calculator, so to speak. You know, I have love for this thing. Actually, so this isn't the one I'm holding right now, but I'd really recommend getting a TI-89. Thing pays for itself, actually. So this angle is about, that's approximation, so it's about 32 degrees. So that is the minimum angle. And for real life situations, say that you only had a certain amount of length. Well, if you had a lot of length, you would have a, obviously your angle here will be much greater than this. But say you didn't have enough length, well, you wouldn't want your angle to go smaller than this 32 degrees. Say it was 30, well then your rope snap, your cement tube falls, and then you're done. But no, this is in fact the smallest you can go. So once again, word to my sponsors, you guys go ahead and check out Contest Celebration and make a profile. Get on there and win that $500 that they do a month. Alright, up and out.